I am Keshav Nahar from Stage 2. Topic of presentation is the dining philosopher problem. So let's start. The dining philosopher problem. The dining philosopher's problem is a classic computer science problem that illustrates the challenges of achieving deadlock, avoidance, and resources allocation in concurrent system. It involves a group of philosophers who must share a limit number of forks to each their meal. Deadlock and starvation. Deadlock. The dining philosopher problem can lead to a deadlock situation where each philosopher hold on for and is waiting for another, resulting in a circular wait and preventing any philosopher from making process. Uh, Here is the diagram how process and starvation work. If the forks are not distributed fairly, some philosophers may continuously be denied access to the forks, leading to a starvation scenario where they are unable to eat. Process solution. Asymmetric equations. Philosophers could be instructed to always pick up the fork in a specific order, preventing circular wait and ensuring deadlock avoidance. Hierarchical allocation. Forks could be assigned properties, and philosophers would only be allowed to pick up fork in order to decreasing property to prevent deadlock. Randomized acquisition. Philosophers could be allowed to pick up fork randomly, which would statically reduce the likelihood of deadlock but not guarantee it. Implementing a situation. Here is the diagram how they work. Acquired forks. Philosophers must acquire the necessary forks before beginning to eat. Second is release fork. After finishing their meal, philosophers must release the fork they were using. A third one is repeat. The cycle would acquiring and releasing fork must be repeated for each meal. Resources allocation synchronization. Here is the diagram. The dining philosopher problem highlights the importance of resource allocation and synchronization of multi-threaded environments. And this is cross solution. This is cross solution used to a same Semford to ensure that only limited number of philosophers can eat at a time, preventing deadlock. Semaphore, a synchronization object that control access to share resources. Philosophers algorithms. Each philosopher pick up the forks on their left first, then attempt to pick up the fork on their right. Semaphore signaling. A philosopher release the semaphore where they have finished eating, allowing another philosophers to acquire the solution. Advantage and limitation of disease crash solution effectively address the deadlock issue, but it also has some limitation. Advantage: eliminate deadlock and prevent starvation by ensuring that only a limited number of philosophers can eat at a time. Limitation: can be completed to implement and may introduce overhead. It does not address potentially for fairness issue in resource allocation. Conclusion and takeaways. The dining philosopher's problem provides valuable insights into the challenges of resource allocation and synchronization in concurrent system. Importance of synchronization. Synchronization mechanisms are circular for preventing deadlock and ensuring fairness in resources allocation. Deadlock prevention. Various solutions such as disease crash solution can be used to prevent deadlock in concurrent system resources allocation. The dining philosopher's problem highlight the need for careful resource allocation strategies in concurrent system. Thank you.